In this video, we're going to talk about trigonometric integrals. So we've done a few using u substitution back when we did some u substitution, and we did a few using integration by parts when we did the reduction formulas, for example. But this is going to be a little bit further into the different ways of integrating trigonometric functions. And so there's actually very little theory here that's new. Mostly we're going to be basing ourselves on trigonometric identities, which you may or may not know from high school, some of them. So some of those might be new to you, but you might actually know those from high school. And then we're going to be doing things exactly like that, trigonometric identities plus some u sub that we'd done before. So this is going to be split up basically into three parts. Part one is going to be powers and products of the sine and the cosine function. Part two will be something similar, but with secant and the tangent functions. And then part three will be other trigonometric integrals that don't follow the nice patterns that we get in parts 1 and 2. So we're going to go ahead and start now with the powers and products of sine and cosine. And so let's start first by looking at simple powers. So cos of x to the nth power and sine of nothing, apparently. Oopsie-daisy. Sine of x to the nth power as well. So method one would be what I had just mentioned, reduction formulas, right? So we had done some reduction formulas, and that is fine. Reduction formulas will handle anything of these forms, but you obviously, to use a reduction formula, you have to know the reduction formula. So if you are an ace at memorizing, then fine, go ahead, but be aware that I can specifically ask you not to use a reduction formula, and so you do absolutely need to know how to do this method 2. And that's the method that we're going to cover now in this video. So the second method is going to be based on relationships between the sine function and the cosine function. And there's two main kinds of relationships that we're going to be talking about. The first is the derivative relationships, right? We know that the derivative of sine is cos, and the derivative of cos is minus sine. So those derivative relationships are going to come in handy, especially when we end up by doing the u subs that we're going to be doing after. The second big ingredient are relationships between sine and cosine that we're going to need are trigonometric identities. And so the most famous one, the one that everybody always remembers from high school, is sine squared theta plus cos squared theta equals 1. That is typically called the Pythagorean identity. And then the second group of identities that are less commonly known, so you might have seen these in high school, you might not. They are called the half-angle identities, and there are two of them, one for cos squared actually, and one for sine squared theta. And the half-angle identities are these. So cos squared theta is equal to 1 plus cos of 2 theta all divided by 2. And sine squared theta is equal to 1 minus sine of 2. That's not true. Whoops. Oh my goodness. I should read these things over before I start my videos. 1 minus cos of 2 theta. It's nice to see, though, that I make the same kind of mistakes in videos as I would have in class, though, for you, hey? Brings things back to earth. Okay, so those are the two half-angle identities that we are going to use along with the Pythagorean identities and the derivative relationship. So we're going to put all of these things together to deal with these kind of integrals. And so the first thing The first thing that we're going to look at is cos squared. That is a power here of cosine. And the rest of this video is just going to be examples of how that we put these different relationships together. Okay, so we're just going to do a whole bunch of examples of these different cases. So the first one, cos squared of x dx. So the easiest and simplest way to do this, especially by hand rather than memorizing a big old reduction formula, is to use the half angle identity. The cosine squared of x can be replaced with 1 plus 2 cos x over 2 dx. And then now that's something that we can anti-differentiate. The 1/2 comes out, right? That 1/2 comes out, leaving us with 1 plus cos 2x. So to now anti-differentiate, right, the antiderivative, or the easiest antiderivative of 1 is x. Cos of 2x, we are going to start moving into doing what I call mini substitutions, and we're going to do these in our head, right, which is partly why it's in a thought bubble. I would not usually write this down. So for an easy substitution like this, an easy substitution where you end up by getting, yikes, another mistake. Let's get rid of that x there. An easy substitution where you end up by getting just some sort of constant multiple of dx, right? There's an easy derivative there. Then I would just sort of do this in my head and realize that this constant multiple is going to turn into a 1 over in front, and I would just write it. So in examples going forward, these kind of mini substitutions, right, this whole big thing that you would normally have written a couple weeks ago when we did u substitution, I will not write now. I will simply do a mini sub in my head and write down the answer. So there it is. If we multiply this 1/2 through, we get the general antiderivative as our answer, 1/2 x plus 1/4 sine 2x plus c. That's example 1. Example 1 using these half angle identities, right? That one there. Example 2. It's again a power. But now the power is a little higher. So the half angle identity doesn't apply, at least not directly. So what we can do, of course, is modify this power using a law of exponents. Sine to the 4th of x can be written as sine squared of x squared, right? So that's just a little law of exponents. And why would I use that law of exponents? Because now inside the bracket, the half angle identity does apply. Right? And so for the sine function, our half angle identity is almost the same as the cosine one, except the term in the top has a minus instead of a plus, right? The cosine one plus cos of 2 theta, the sine squared one minus cos of 2 theta all over 2. So I replace the sine squared with 1 minus cos 2 theta 2x over 2. And then what do I have to do? Well, I have to take care of this square. And so this is going to be something that we have also done in the past. One of our toolbox techniques. We are going to expand that square. If we expand that square, the 1/2 becomes 1/4 in front, right? 1/4, 1/2 squared. Expand the square and you get here 1 minus 2 cos 2x plus cos squared 2x. Now this part is fine, right? We can anti-differentiate that. This part is fine. We can anti-differentiate that. But what do we do over here? We have another squared. Well, so what that means is we go ahead and do the half angle identity again, right? So we're doing it twice. The half angle again, right? So we've done it once, now we're doing it twice. But we've got to be careful. When we did it the first time, first of all, we had a sine, but more to the point, we only had x. Now we have 2x. So we have to be careful about that. We're doing the cos squared. Let's call it theta. Here's the cos one, so we have a plus there. And if our theta is 2x, and we plug it in here, then 2 theta, right? 2 theta becomes 2 times 2x. So we end up by getting this here. This ends up by being the cos squared of 2x. So that is what goes here in the trig identity there, that formula. And now we've got everything in its easily anti-differentiable form. So we're just going to clear up some constants. So I'm going to put everything over 2, right? If I put everything over 2, then this guy would become a 2, this guy would become a 4, and then I pull out the 1/2 and I get 1/8, and this is what's left upstairs. Collect your constants and you get 3. Minus this guy stays the same, this guy stays the same, and then what happens? What happens are just mini subs, like I was talking about upstairs, further up. So antiderivative here, the 1/8 comes down, 3 becomes 3x. Mini sub here, we divide by 2 because of this 2 right here. Antiderivative of cos is sine. The 4 makes me divide by 4. Antiderivative of cos again is sine plus c, and there is our final answer with the 1/8 multiplied into everything. Next example, so let's bump up the difficulty one more level. Sine to the 4th, now sine to the 5th. So sine to the 5th does not work as easily, right? What was so nice about sine squared was that when I wrote the law of exponents, inside became something that I could use a trig identity for. Well, that's not going to happen here because this is an odd power, and the trig identity is a square and so works with even powers. And so what happens when you have an odd power? You've got to play a slightly different game, So what is the technique with odd powers? The technique with odd powers is to do this, which is again a different law of exponents, here. And that law of exponents lets me pull out one factor, right? That is like sine of x to the 1. 4 plus 1 gives me 5, right? So that is a different law of exponents, and that law of exponents is going to let me do yet a different kind of manipulation for these functions. So I'm going to use the first law of exponents that we used as well to write sine to the 4th as sine squared, but this time I am not going to use, right, the Pythagorean identity. We had 2. We had this new one, right? I am going to use the Pythagorean identity. Sine squared, we had just seen this half angle identity, 1 minus cos 2 theta over 2. That is true. There is another identity. If I use the Pythagorean identity, then sine squared is 1 minus cos squared theta. Both of those are true. And I am choosing in this instance to use a different one. So that the sine squared, this time I'm going to replace by 1 minus cos squared, not by 1 minus cos 2 theta over 2. Why? Why would I do that? Because I know what's coming. Because I have done this tons, and I can see that if I use this kind of formulation, then that allows me to do a U sub. That yellow does not show up very well, but that allows me to do a U sub. And if I do that, if I say, well, let's let U be cos theta, not cos squared, just cos. Let U be cos theta, then du is minus sine theta d theta. And guess what is sitting outside? I keep saying theta. Oh boy, a cos x, and du is minus sine x dx. Guess what is sitting right outside there? There's sine x dx, right? It's set up for a u sub, and this is not a mini sub, right? This is not a mini sub. This is a full u sub, a full u sub. So this kind of thing I want you to write. It's not just a constant multiple, it's a full u sub. So you will write this on the side, and then it's just a u sub, right? All of the complexities, all of the new stuff that we hadn't done yet is in the first steps. Once you get to the u sub, it's just a u sub, right? So if you plug that in, we're missing the negative, so that negative comes outside. The 1 stays. Cos of x is u, so cos squared becomes u squared. The square stays, and all of this just becomes du. Then, my friends, it's old. It's what we've done before. So what are you going to do with that square, right? This square right there, you expand. You just expand it. Here is the expanded form. That now is just a power rule, right? That is a power rule, so you do the power rule on each of those u's. You multiply in the negative signs, and you revert to x, right? So the part in blue is a new manipulation, a new sort of preamble to the problem. And once you get down to this part right here, it just is what we've done before, okay? So there's a couple more examples of this sine and cosine, and then I will do tangent and secant and the other in another video. So what happens instead of a power, right? Everything that we were looking at before was power. Well, what if we have a product? What if it's a product of sine and cosine? And as it turns out, what we just did up here, right? What we just did up here by pulling out, right? What we did is we pulled out the du. That is what we did. We pulled out the du. What do we mean by pulled out? This factor here. That factor there is the du that we pulled out, right? That's what became the du. That idea of pulling out the du is exactly what you want with the product of sine and cosine. So in fact, there is nothing different in this example except what we start with. So if we start with the indefinite integral of sine to the 4th, cos to the 7th, then I am going to pull out one of those. I'm going to pull out one of those, and the one that I'm going to pull out is the one that had an odd power. The one that had an odd power, I pull out what is going to be du, right? Du is going to be my cos of x dx. That's what I'm thinking of in a head. All right, so then what's over here, the even powers, well, the even powers play nicely with squares, and the squares play nicely with Pythagorean identities. That is why we pull out an odd power. Pull out the odd power, and then if we're thinking that the odd power becomes the du, I have to identify what should be the u. Well, if cos is the du, then the u should be sine. Then the u should be sine. And if u is sine x, then du is cos x, and everything works. But that tells me what to do in my next step. If u is going to be sine, then I want to rewrite all the remaining functions, not the du, right? The du will stay. The du will stay as cos, but I will rewrite everything else in terms of the sine, because that is what I want to replace for u. Okay? So once I have done that, right, then everything just gets replaced by u. Once you've identified this, right, the du and use the correct identities, everything past here is just a u sub. Okay, so this part in green, just like that part in blue up there, this part in green is the trigonometric part, and then the rest of it is all just u substitution. So let's just follow through that u substitution really quickly now. So this sine is u, so sine to the fourth is u to the fourth. 1 minus sine squared, this was a Pythagorean identity. Cos squared became 1 minus sine squared, so 1 minus u squared. And then the cubed power stays, and then, you know, it's just what we did before. Then you are going to expand. You are going to expand, and then you are going to use the power rule, and then you are going to revert. So this part is from earlier in term. So we've seen a whole lot in the sine and the cos of different things to do. Let's just look over the summary of this, and the summary is the following. So for powers and products of sine and cosine, so we can write them like this, and you can say, hey, that's a product, there's no power there. Well, wait. If one of these things is 0, then what's left is a power. So this general form covers both powers and products. So the general or the summary rule here is if m or n are odd, if m or n are odd, then what you are going to do is what we just did in the last example. You are going to pull out one copy of the odd power to serve as the du. You are then going to use the Pythagorean identities to rewrite the remaining functions accordingly, and then do a u sub. Okay, that is if the m or n, if there is at least one odd power, you will do this procedure. If, however, both m and n are even, both, if one of them is odd, you're doing this. If both of them are even, then you have no choice but to apply the half angle identities, and perhaps repeatedly. Right? So you have to do a laws of exponents, and then all of these identities, and then expand them, and then reapply them. So when both are even, there's a lot more work involved here, but it is entirely manageable to do by hand. Okay, so that is the products and powers combinations of the sine and cosine. So we're going to leave it there for this video. In the next video, we're going to come back and look at the powers and products of the secant and tangent, which is going to have a whole other sort of set of rules and situations.